Good morning. My goal here is to go through this chapter on the book on low pass filters. This is actually the 11th edition of Nielsen. I think it's very readable and easy to go through. Rather than create a bunch of independent PowerPoint slides that maybe leave certain things out, I just want to step through what's in your textbook and look at some examples that basically mirror what we're doing in the lecture and class. The first thing I want to do is let's go back and let's look at some of the fundamental definitions of a filter. Remember, in a filter circuit, we have an input and an output. Now, it's a little confusing in this part of your book. They're actually showing the input as a physical source. That's fine. That's just there for you to understand that there is some kind of input. But remember, the actual filter circuit itself does not include the source. It's basically the circuit between the input source voltage and the output voltage that we're interested in. And what the filter is going to do is it's going to do some things to the signal as far as its frequency is concerned. So a little bit of preliminary stuff. Often in frequency selective circuits, which are also known as filters, we have some definitions. The part of the signal that manages to make it to the output occurs within a frequency band that we refer to as the pass band. The frequencies that are blocked from reaching the output are in a range that we refer to as the stop band. And basically, what kind of filter you have depends on what kind of pass band you have. And so in order to determine what circuits and filters are doing in the frequency domain, we basically have two different kinds of visual plots we can look at. One is a graph of the magnitude of h of j omega, which is the output over input as a function of omega. That's referred to as the magnitude plot. And the other is the phase of h, which we refer to as the phase angle plot. Now, ideal filters have some unique characteristics. If we look at this figure 14.2, this is an ideal filter. And notice the magnitude plot. In the pass band, we have an output of 1. Now, what does that mean? That means that the output voltage is equal to the input voltage. So for a certain range of frequencies, the output voltage is equal to the input voltage. And then suddenly that ratio stops abruptly and becomes 0. So there are some unique things about an ideal filter. One is that it is flat and equal to 1 in the pass band. So output voltage equals input voltage in the pass band. The other is that output voltage equals 0 in the stop band. And the third thing about ideal filters is that there is an infinite change or an infinitely steep change between the pass band and the stop band. So the transition has a vertical slope. The phase plot, you'll notice, has a linear slope. This is called the linear phase function, and that's significant if you're trying to reconstruct signals that have gone through filters. So this particular example is referred to as a low pass filter because it is passing voltages, or the pass band is located on the lower end of the frequency spectrum, coming all the way down to 0 or DC. And then in this case, we have what we refer to as a high pass filter because the pass band occurs in the higher frequency range and the stop band occurs in the lower frequency range. There are some additional kinds of filters that we'll get to later. One is referred to as the band pass. The band pass has its pass band located between two frequencies, omega C1 and omega C2. Omega here is referred to as the cutoff frequency. So all filters would have a cutoff frequency. In the low pass, omega would be the upper limit. In the high pass, omega would be the lower limit. In the band pass, you actually have two cutoff frequencies, a lower and an upper, that define the pass band. The band reject is basically the opposite of the pass band. In the band reject, you would have a region in here where you do not pass a range of frequencies, but you pass everything else. So it's like a combination of the sum of a low pass and a high pass, whereas um, the band pass would be like a combination of the product of a low pass and a high pass. So let's look then and review the low pass filter. So we saw what an ideal filter looks like in the most simple terms. We're going to talk about first order low pass filters first. First order is going to mean that when you find the transfer function of the filter, you only have one pole in the denominator. So S, it just occurs as a first order polynomial. So let's move ahead. Let's come back. This is our example for an RL filter. Here is the circuit in the just drawn in the time domain. If we think about it, when we have a zero, we have DC, the inductor looks like a short, and so we would expect all of the voltage to drop across the resistor. When we have very high frequencies, the inductor or j omega L looks like an open, and we would expect the voltage to drop across the inductor, voltage across the resistor then going to zero because there's no current. So that's explained here in the text that as the frequency increases, the impedance of the inductor increases relative to the resistor, and so you would expect to see your voltage drop more across the inductor. Here's what, before really doing any mathematics, here is a picture of what the frequency response plot looks like for the series RLC low pass filter first order. You'll notice that for a very brief range of frequencies or a very narrow range of frequencies, we are sitting at 1, and then it immediately begins to fall. Here, omega C, the cutoff, is defined as the point where the magnitude of output over input is 1 over the square root of 2. So this point would be 0.707 because we know we don't have an ideal filter. So why is it not ideal? The magnitude ratios in the passband are not equal to 1. The transition is not infinitely steep or vertical. And in the stop band, we have regions where the magnitude is not equal to 0. Notice also the phase plot is not linear with respect to omega. So once again, here's the definition of the cutoff frequency. And let me just interject that this cutoff frequency definition occurs across all types of filters. It is a general definition. So for any filter, the general definition is that the cutoff frequency is 1 over the square root of 2 times the maximum value of the transfer function. The maximum value of the transfer function is in general considered to be 1. There is often what we refer to as a gain, but in this case, the gain is not considered when evaluating the transfer function. So we will talk about systems that have a gain or an attenuation shortly. So this is just some stuff about how the cutoff frequency is the maximum power transfer. All right, so let's get to the mathematical analysis. The transfer function of the RL low-pass filter can be written as shown here. You can get this by writing a voltage divider ratio of V out in terms of Vn, doing some mathematics, and you'll basically end up with a transfer function that looks like this. Now, in order to evaluate the frequency response, as we discussed in class, we basically substitute j omega for s. So making the substitution, s goes to j omega. Here's what our transfer function looks like when we're discussing the frequency response. So once again, this is not the transfer function in the Laplace domain. This is the transfer function where we have decided that we will not consider, we are only interested in the frequency response. So we let s go to j omega so that we can evaluate it as a function of frequency. Now I want to point out here that this this function can actually be used to calculate the value of the transfer function at any value of omega. So if I had given you values of R and L and I asked you to find the output for omega was 20 radians per second, you would just plug in 20, you would get a complex number with actual values, and then you could calculate the magnitude and phase. Now at this point, because this is a complex equation, it has two components. One is the magnitude and one is the phase. And so that's calculated right here, where we find the magnitude by taking the square root of the sum of the squares of the imaginary part and the real part. And we find the phase. Note that the phase in the numerator is 0 degrees. Phase in the denominator is the inverse tangent of omega over R over L. So you do a little bit of mathematics and you end up with this expression for the phase. So this is some discussion about magnitude plot we saw before. Notice that when omega is equal to 0, the numerator and denominator in the magnitude are equal, meaning your transfer function would have a value of 1. Notice that as omega gets very large, the denominator is going to dominate and become very large with respect to R over L. And so the transfer function value is going to go to 0. If we wanted to find the cutoff, we could let the magnitude of h equal 1 over the square root of 2. If you do that and do some algebra, you find that that occurs when omega is equal to R over L. So the cutoff frequency for RL filters, omega is equal to R over L. And this is an important result because basically this allows you then to design a low-pass RL filter. So in fact, in your textbook, there is a little bit of a design problem. It's talking about electrocardiography or ECG. In an ECG, your normal heartbeat is about 72 beats a minute. That means you're detecting the signal that occurs about once a second, which would be a frequency of 1 hertz. So in this problem, you're asked to choose values for R and L, where you could filter out any noise that occurs above 10 hertz. Why is 10 chosen? That's kind of an arbitrary choice, but certainly we know that in a normal lab in the United States, we have 60 hertz noise everywhere because that's the power frequency. So we would like to get rid of that 60 hertz noise, so 10 hertz is just kind of a number to choose. So we want to choose R and L, design this circuit, and then we want to look and see what is the magnitude of the output at 1 hertz, 10 hertz, and 60 hertz respectively. So usually it's a good idea to choose a commonly available value of the inductor because it's going to be the more difficult one to locate. So in this example, a 100 millihenry inductor is chosen. And then based on that and based on the known desired cutoff frequency and the fact that we would need a resistor that would accomplish that, we need to solve a couple of things. First of all, it is extremely important to remember that in our design and our equations, we are talking about omega in radians per second, not hertz. So that 1 hertz or that 10 hertz before we can do anything else needs to be converted to radians per second. So you see that done right here. Omega C is changing our 10 hertz. That is a multiplication by 2 pi. If you still don't know how to change from radians per second to hertz and back, it is really something you need to learn now. So to get from F to omega, we multiply by 2 pi. So 20 pi radians per second is our design term. We know that 20 pi radians per second has got to be R over L. So we can solve for R, and when we do that, we get 6.28 ohms. So now the problem asks us to calculate the magnitude at 1 hertz, 10 hertz, and 60 hertz. So here's the expression for the magnitude of the output voltage as derived earlier, and R over L are known, so we can plug in 20 pi for R over L and 400 pi squared for R over L squared. And then Basically what you would do is you would plug in the three different values of omega and calculate the result. And if you do that, that's shown here. So for 1 hertz, our output over input is 0.995, which is very close to 1. For 10 hertz, it is 0.707, which is exactly cut off. And for 60 hertz, it is 0.164. So you can see that once we pass this 10 hertz, we fall pretty rapidly, attenuating. We're getting about 16% of the magnitude of 60 hertz noise that we would normally pick up. The other type of low-pass filter is the series RC. Just to look qualitatively at the series RC, we know that at DC or zero frequency, this capacitor looks like an open circuit. So all of the output voltage, basically the output voltage, would equal the input voltage. As we then begin to increase the frequency, remember the impedance of the capacitor is 1 over j omega c. So as omega gets very large, that approaches a short. So at very high frequencies, the capacitor will look like a short. All the voltage will drop across the resistor, and we will get no output voltage across the capacitor. So the transfer function for the series RC is actually done as an example in this book. So basically, to derive an expression, we put this in the Laplace domain. We then, taking our output voltage across the capacitive impedance, we then write the transfer function using the voltage divider rule. And at that point, now we have h of s as a function of s. Now we want to evaluate the frequency response, so we're going to substitute s with j omega and compute the magnitude and phase. And so that's done here, missing a few steps. So you would substitute j omega for s, just like we did in class, calculate the magnitude, and this is the expression you should get. The cutoff frequency, you let this magnitude equal 1 over the square root of 2, do a little algebra, and you find that that occurs when omega c occurs at 1 over RC. So the cutoff frequency for RC filters, 1 over RC. So once again, if you're asked to find a filter with a specific cutoff frequency, in this example, you were requested to find a cutoff frequency with 3 kilohertz. So the first thing we would do is we would take 3 kilohertz and multiply that by 2 pi so that we get that in radians per second. And then we could choose a capacitor with a normal value of about 1 microfarad. So choosing 1 microfarad and plugging in our frequency, rearranging our equation so that we can solve for R, we find that we can design a 3 kilohertz low-pass filter by choosing a resistor value of 53 ohms. So the transfer function for low-pass filters can be written in a general form. And the general form is that the transfer function, h is a function of s, is equal to the cutoff frequency over s plus the cutoff frequency. So this does two things for you. One, if you put your transfer function in proper form, meaning your s has a coefficient of 1, then you will be able to read off the cutoff frequency, and it is best to usually do that in the denominator, just in case you had something that created some sort of gain or attenuation. In a passive filter, which means a filter built just from passive elements, resistors and capacitors, you won't have that. But in an active filter, you can. So you look at the denominator, you can easily identify the cutoff frequency by whatever number shows up here. You can also identify the fact that this is a low-pass filter because there's no S in the numerator. All right, so here are the two low-pass filters shown together, the RL and the RC, along with their equations, their transfer functions, and their cutoff frequencies. So this provides a nice summary of the equations associated with the two low-pass filters, as well as the low-pass filter design.